In this work, besides studying the kink perturbation, we have studied the kink-anti-kink collision. The most common ansatz for starting the collision is putting the kink-anti-kink in this form, okay, which is called additive ansatz. Then the most common scenarios is after the collision, you have 3 different cases based on the initial velocity of the kink and anti-kink. If the velocity is higher than specific value, which is called critical velocity, then they simply reflect, which is the scenario C, okay? Besides reflecting, they start oscillating and part of the energy will be radiated away. These oscillations you see, it's mostly the vibrational mode, which is attached to the soliton and anti-soliton because it's a bound mode. If the initial velocity is small, then the scenario is they start oscillating, creating the bounce, the bion, which is the bound state of kink anti-kink, and each time radiating part of the energy till they disappear, so it is annihilation. But there is a middle scenario, which is scenario B, which is possible. They create this bion, they collide a couple of times, kind of bouncing couple of times, and then being able to separate, or having the first scenario, which is the annihilation, okay, depending on the initial velocity. This scenario, that the middle scenario, where the initial velocity is enough for them to separate, gives you something called resonance windows, okay? So, as I said, in kink anti-kink collision, the common scenarios is annihilation, resonation, and reflection. Then, for example, this is actually in this model that I'm showing it in our toy model is quite close to lambda 5-4 model. The first graph on top, it is the final velocity as a function of initial velocity. This is exactly what I call which is known as resonance windows. Whenever the blue lines or blue curves, they disappear, it means that they annihilated, okay? So you can see that after specific value, from specific value, which is close to 0.3, after that there is just reflection. And for really small value up to 0.20 something, they always annihilate, but there is middle scenario in between, which is they can reflect, which is the blue lines that appeared here. This is the resonance windows. Or in the middle, there are velocities that they simply decay. Then you can see that if each of these window that we see, if you look at them one by one, when you increase the window number, you go from one to the next one. If you look at the field at the center, you can see that it appears some oscillations, and with the window number, the number of oscillations at the center increases. But this is not that difficult to explain, because the kink and anti-kink, they like they would like to collide because the force between them is attraction. But then it depends on the initial velocity, how much kinetic energy they have, okay? So if you increase the kinetic energy, for them it becomes more difficult to collide again or to bounce again. And each time it becomes more and more difficult, so the period in the middle increases, so the number of these oscillations in the middle increases. Up to the point, like here, n equals 10, that after that it becomes impossible to bounce again, and they simply reflect, which is the scenario of the reflection after the critical velocity that you see. And this frequency of the oscillation at the center is the oscillational frequency that we considered as our normal mode, which is the shape mode or vibrational mode that we have. Okay, so you see that it matches that frequency. So which is given by this relation, this omega t equals a phase shift plus 2 pi n. So if you look at the graph of the period as a function of the window number, each time, as we said, with the window number, the number of oscillation increases by 1. So the relation between them will be linear, which is given by this relation, omega t equals delta plus 2 pi n that we have here. So now let's compare the normal mode and quasi-normal modes that we were discussing. For epsilon equals 0, epsilon encodes the information about delta gamma and delta L, which was related to the barrier size. The depth was given by delta gamma and the width was given by delta L. And epsilon encodes both information. So when it is 0, it means we have normal mode, and when it increases, it means the effect of the barrier gets stronger. So you go gradually to the direction, direction of quasi-normal modes, and the effect of quasi-normal mode increases when you increase the epsilon. So then you can see, at first, when you have just normal mode, the resonance windows, you can see in the first graph on top, which is it has this resonance windows. It is much more thing happening here. But when you increase the epsilon, you see it becomes more and more desertish. Okay, and the critical velocity increases, which makes sense because what's happening is actually what's happening in this, it's called the Campos energy exchange mechanism, which is approximate explanation for what's really happening in these scenarios. So if you imagine you have the kink and anti-kink with kinetic energy with a specific velocity getting close to each other, then this kinetic energy, when they create bound state, can transform to this vibrational mode, which is a bound mode on each soliton, on each kink and anti-kink. And then this can transform back to the kinetic energy and separate if the kinetic energy is enough in the beginning, okay? But the middle scenarios, it means that if the timing is right, you will have the separation. But if it is not right, it means that they start decaying in the middle scenario, which is middle velocity. So here, if you have the quasi-normal modes, it means that the energy start leaking. So if the energy leaks, in the whole process of transforming energy from the translational to vibrational, and then getting back to translational becomes more difficult because the energy radiates away and leaks from the system. So it means that you need higher initial velocity to be able to have that scenario of reflection. Because of that, the critical velocity increased. And in the middle, you see multiple bounces becomes more and more difficult, okay? Because again, because of leaking of the energy, it is when the energy leaks, it becomes each time more difficult to have enough energy to get back again and again. So you will lose many windows here for the reflection. But then it is a known fact, for example, for phi-4 theory, consider phi-4 theory, that if you look at this final velocity as a function of initial velocity, these resonance windows, they have fractal structure, which means that at a smaller, if you look at the system and then look at the system in smaller scales, it repeats itself. So this is known as, if you have a 2 bounce window, next to it there is a 3 bounce, next to 3 bounce there is a 4 bounce, and it continues. So as much as you zoom in, you will see more of these details happening in the middle. And this repeats itself. If it does, then you can find the fractal dimension. For example, if you look at the first graph on top, and then we zoom in and we see the whole graph in the second one, then you zoom in the middle and you get the third graph, and then you see that this is somehow repeating itself. Here is more qualitative version, but then we calculated quantitatively the fractal dimension. But when you increase epsilon, which means when normal mode turns to quasi-normal mode, at first you see it looks like it repeats itself, but at some point when you zoom in more and more, you see that it becomes desertish, it becomes poorer in the structure of these resonance windows. So it means that it loses the fractal structure, and if you increase epsilon more and more, you will see this happen sooner and sooner. Then we try to quantify this fractal dimension. This fractal dimension, you can find it this way. Imagine I divide the whole region in boxes with the same width, okay, which is the length of this width is given by this L. Then how many boxes are needed to cover these resonance windows out of those total ones? And when you take the limit of the box width going to 0, you get the fractal dimension. But this is computationally is really costly. So what we did was we got smaller and smaller region, but we didn't pick the same box and making the size of each of the small pieces smaller and smaller. Instead, we picked a smaller box and then calculated this dimension as a fit, okay? And then we see that when you get different regions in different scales, you see for the normal mode, we get almost the same if you have the graph of log of this number of boxes that cover these resonance windows over log of this the length of each box in the beginning, okay? If you calculate, you see the slope is fixed in different regions when you get to smaller and smaller region for the normal mode when epsilon is 0. But when you look at the epsilon non-zero, at first it looks like that it keeps the slope, but then you see that gradually the slope changes, and then the slope gets closer and closer to 1. You can see in this table for the epsilon equals 0 the first tree, and epsilon equals 0.005 for the second tree. And you see that at first it seems that the slope is similar, but then when you zoom in more and more, you see that the value of this slope becomes closer to 1, which is the dimension of a line. So it becomes closer and closer to what you expect from a line, which is not a fractal dimension. So this proves that when you have quasi-normal mode, gradually you lose this fractal structure, and actually fractal is in the limit of L going to 0. So in principle, when epsilon is non-zero, at some point you will lose it. So you will lose the fractal structure. So, so in the whole process of this collision, what we learned was because due to this energy leak that we have in the system because of this quasi-normal mode, the critical velocity for the reflection increases as expected. Then the fractal structure or self-similarity is gradually lost when you increase epsilon, which means when you turn the normal mode to quasi-normal mode. This is the main result of this work, okay? Then besides this work, we did another work in this line of the collision of the kings. there appeared something since last year that people were thinking all types of kinks. You can do the collision with these additive unsoughts, but then people understood that, for example, there appeared something really strange in the case of, for example, for phi 8 model, okay, which was the kink and anti-kink, instead of attracting each other, which is the expected result, they saw that they are repelling each other. So gradually, with the results that people got during these years, they got that the results are really strange in this case. Then they understood that when you have kinks with long-range tail, with one or two long-range tails, the way you treat the system couldn't be the same as normal soliton like phi 4, okay? Because the kink itself, for example, for phi 4, if you look at the tail, it is exponentially going to the asymptotic value, like tangent hyper. If you go for large x or large positive or negative x, it exponentially converges to the asymptotic value. But if you pick, for example, phi 8 or phi 10 or phi 12 for phi above, with the power above 6, you can see that this is not valid anymore. The tails, they start going to that asymptotic value really gradually. They go to that asymptotic value power law instead of exponentially. What does it mean? It means when you have the collision, they will see each other for a long range. They will overlap for a really long range. Then people understood that. So it means that they are highly interactive. So they don't need to be really close to interact. They can interact from large distances. So you should be really careful how to start the collision. And people understood that the simple additive unsoughts that we used in the other model, this doesn't work with the long-range tail kinks in the collision. So what people studied was, actually this whole thing appeared since last year, 2019, that appeared in Manton's paper, that how to treat the system if you have the long-range kinks. And then after that, Christoph et al, they could come up with the idea how to start the system for the numerical simulation, how to put them together for the collision. Then what they understood was that you need to treat the system differently. For example, in Manton's paper, what Manton suggested was, let's consider, instead of kink and anti-kink, let's consider just a kink, one accelerating kink. We don't care this force is coming from anti-kink. We just look at the kink, okay? And in this kink, he used he used the slowly moving kink, so made some approximation. If the kink is slowly moving, then could use the BPS condition, because BPS condition is valid for static case. But if the velocity is small enough, you could consider the system close to static, so you could consider the BPS condition. And then he solved the system like this. So let's see how this works. The system we considered is it's phi to the 4n class of system, but what we in practice we consider it's for n equals 2, which gives phi 8 theory, and n equals 3, which is phi 12 theory. Then always you can do it in 1+1. You relate it to this superpotential as I introduced before. So you can find in this model the superpotential, the C1 and C2 that comes from this integration. They don't matter for the rest of the calculation. So without loss of generality, we could put them equal 0. Then the BPS condition, as I showed you, it gives the first derivative relates the first derivative of phi to this superpotential. Then when you solve it for our model, you get two implicit relations written here. Actually, it is not known how we can solve this explicitly. So it means that if you want to solve it, then you have to do it numerically. And if you calculate the mass of the soliton will be related to this superpotential at the boundaries, okay, the subtraction. And I wrote the result of it for both cases, the phi 8 model and phi 12 model. This is the interesting part. You can see that the potential, as I showed for the phi 4, close to the minima is not as flat as these models, okay? This is actually the origin of having long-range model, okay? You will see that the model is symmetric, so it has long-range tail in both directions, so it takes a large distance to gradually go to that asymptotic value, which is 1 and minus 1 with the rescaling that we did here. So in the phi 8 model, you can see that if you do the expansion around each minima, you will see for phi 8, the first non-zero derivative is fourth order. So the second and third derivative of v around this minimum is 0. Okay, so it starts from fourth, and for phi 12, it starts from 6, okay, which is exactly the point of having long range, okay. For example, for the phi 4, it's quadratic, okay, so it is non-zero from the second derivative of the potential around this minimum. So let's see how Manton suggestion worked. So if you look at the tails, you will see that for phi 8, it goes 1 over x, which is power law, and phi 12 is even worse. It goes slower than phi 8 to asymptotic values. Then let's look at the equation of motion. This is Manton's ansatz, that you could consider the field to be in the shape of the accelerating kink to be in the shape of eta of x minus at. A is the center of the kink. This is a moving kink, accelerating kink. Then considered slowly moving kink. So disregarded the a dot contribution here, because we want to instead of working with phi here, we want to work with eta here, one accelerating kink. If you put it in this equation of motion and ignore a dot term, you will get this relation, the second order derivative relation for eta. And then if you are working with slowly moving kink, then it is valid to consider the BPS condition for eta, which is this eta prime equals dw d eta. And this a is minus a double dot, which is the acceleration. We considered it with negative sign because we know that the kink and anti-kink, in principle, they attract each other. And when we replace this first derivative term inside the second order derivative in eta, you can define V effective, and then integrating it, you will get first order derivative in eta related to this V effective and W at the asymptotic value. Then, okay, you could simply solve this numerically and see how this behaves. But what Manton did, the point was doing this analytically. So he suggested to look at just the long range tail that is facing the kink, facing the anti-kink. So the collision is between kink and anti-kink, and they are colliding from the direction that they are long range. This is, in our case, it doesn't matter because we have double long range, because both tails are long range, so you could pick any of them. But there are models that they are just one side of them is long range. So the point for Manton was looking at the side that it is long range to face the other anti-kink. So then imagine that you look at just this long range tail that's facing this kink, and you ignore the other tail, and you do this approximation. Okay, so you do the approximation close to this asymptotic value of phi. And then when you solve the system, you will find the acceleration, okay? And if you know the acceleration, you know the force. And interestingly, we found the force in this model with the prefactor, this 1.477, and the other prefactor 0.172, and the exponent of this a, which is a to the fourth and cubed. It is exact same thing as the other model with one long range tail that people studied last year. That the interesting part is it exact same thing in that model for phi 8 and phi 10, and the point is the behavior of the potential around the minima, how the derivative of the potential, the expansion, the Taylor expansion around this minimum, how from where it starts not being non-zero, that matters for this prefactor and for the exponent. So in their phi 8 model, it was like ours, starting from the fourth derivative of the potential around this minimum to be non-zero. So we have the same prefactor and the same exponent. And our phi 12 matches their phi 10, which is exactly because ours, the derivative of the potential, the non-zero derivative, it starts from the sixth order. And in their model, the phi 10 has this behavior. So you see that if they have the same behavior around the minima, you will have the same force here. Okay, the same behavior for the force here. But everything here is asymptotic, because I consider you look at the tail that is facing anti-kink and you ignore another tail. Okay, which is in our model is trickier, because when you do the collision really fast, the anti-kink will see other tail and kink will see other tail of the anti-kink. So this is just valid for when they are in large distances. Then we see in the graph, then I will show you that this is valid. For the case of one long range tail, this is a better approximation, because when the long range tails they face, after facing, when they collide, they will face other tail which is not long range. So this really helps for the model not to diverge from the correct result. So this is a really good approximation actually in that case. For our case, it's trickier. So now, if you want to solve the system analytically, we looked at phi 8, for example, and if you do the expansion around the phi equals -1, look around the tail that is facing anti-kink, if you do, you can put the second order term together with the first and define the center of the kink, that A, as a shifted center, okay, and still keeping the shape of 1 over a minus x, which helps us to solve the system analytically. This is possible to do it for phi 8, but this is not possible for phi 12, and then you see that the valid approximations, if you do, then the system is not analytically solvable. So we didn't continue for phi 12 to try to solve it analytically. So for the numerical simulation, what Christoph et al. And the collaborators, what they did, they considered the additive ansatz that we have. As I said, it doesn't work for long-range tail kinks, for the collision of long-range tail kinks. So they came up with the idea of split domain ansatz, okay, which is introducing this Heaviside function to guarantee that the kink effect stays in the right, for example, and anti-kink effect stays in the left. Okay, so somehow you get rid of the effect of superposition of the two. Okay, this is just for the starting point of the collision. Okay, and then you will see that if you do you will get in the derivative, this field configuration will be in the derivative will be discontinuous, and then to get rid of this discontinuity, which is physical system normally doesn't have this discontinuity, they did a minimization. This minimization is simply they wanted to minimize the equation of motion to get as close as possible to zero, okay, which is a valid assumption because it should follow the equation of motion, and the kink to be centered at A and anti-kink to be centered at minus A. So if you separately impose it, the system will be overdetermined, so it doesn't work. So they put together all these conditions in one and minimize the system with this condition. Then for the moving kink, the trick here that they used, and then we made it better, what they did is, let us consider again the field as phi of x minus vt, a moving wave, okay. It's like a boost in the field configuration, and then the equation of motion obviously for u changes to this form, that this equation of motion we have, the last equation. Then, okay, besides the initial guess, initial condition for the field configuration, we need for the velocity field too. So for the first derivative of this field in time, you need an initial guess also, because the equation, when it is moving kink anti, you have moving kink anti-kink. The initial condition is when you have this moving kink, you should consider the equation of motion with the second derivative in time. So you need initial guess for the field and for the derivative of the field in time. So the initial guess for the velocity, you can write it as the velocity times sine of x times u prime, okay? Here, this is doing the velocity, making the velocity of this phi. The sine of x, it's like that split domain on sots. It guarantees that the velocity of the kink is to the direction of anti-kink, and for anti-kink is the other way around, because sine of x changes, so you change the sign of the velocity, you guarantee that. Then again, you will face discontinuity. To get rid of discontinuity, what we came up with, which is highly effective computationally, that you can show that the initial velocity field should be as close as possible to the zero mode of the perturbation around the initial configuration u of x, okay. This is actually, we showed that it works really well, okay. And okay, if you do that, the zero mode equation is given by the last equation here, okay. So this is the condition you need for the minimization, okay, to get rid of the cusp here that you will see, you see here, okay. If you look at the field configuration, you see a cusp in blue line at the center, which was the split domain on sots, and after minimization, which was coming from that nonlinear minimization, that we had equation of motion and putting the kink, the center of the kink at position A and anti-kink at position minus A, you get rid of the cusp, so you smoothen this. Then for the velocity field, when we do the minimization with the zero mode of the perturbation around this initial configuration u of x, you will see that it smoothen out at the center also, okay. Now we need to check if this method is working, okay. The checking point is, it's much easier to work with the initial kink that are not moving. So what you can do is you put the kink and anti-kink at larger distance with zero velocity and let them interact with each other. There is a force between them, so they start moving. And after moving, when they get to specific position with a specific velocity, it should be the same as our method, that you start from moving kink and anti-kink with these minimization procedures for the phi and the velocity field. Okay, so then you can compare the two methods, because the one that you started with the zero velocity, it's completely trustable, okay, which works perfectly. So then you compare the other one, which is moving one, you compare with that one, and if it is matching, your method is correct, okay? So then you see the velocity field on top, it is the result from the stationary kink and anti-kink in the beginning, and after that, because of the force between them, they start colliding, okay? And we are looking at specific position and a specific velocity, and then after that we are looking at the system, okay, after they start moving. And at the same position with the same velocity, you will see that with our minimization method, you get exact same result. Okay, maybe you compare and you think maybe the detail is different, so you can look at it in this two-dimensional graph. You can look at the velocity, the evolution of velocity in both models, okay, and you will see that it's really smooth in both versions, and they exactly match. So actually, when we started working on it, when the guess is not good, we were getting really messy evolution of the velocity, really chaotic behavior. But when we use these two level of minimization for the field and for the velocity field, they get really smooth and exactly matching in the two methods I introduced here. And then you can look at the initial velocity field that in both methods they exactly match, okay, which was the whole point, that we wanted them to match. So the starting point of both, the starting point of our collision, which they start with the specific velocity, and the one which are stationary, and after a while they get to a specific velocity and specific position, at that position they exactly match, okay? And then, okay, for comparing our simulation result with the analytical result that Manton, the modeling that Manton did, and the analytical result, we need to compare them when the velocity is really small, and the best case scenario is when the initial velocity is zero. So this is another check for our model, okay, for our numerical method. So the red line here is Manton method without further approximation. So you look at the first order derivative of that eta that we introduced, and you solve it directly numerically, okay? And you see that it perfectly matches up to some point, okay? And it matches even better for phi 8, which is expectable, because for phi 12 it becomes even more long range, which is called fatter tail, okay? So it starts failing at some point, okay? The dashed black line is our analytical approximation. That was just, we could do it for the phi 8, and you see that up to some point is working, is not bad, and after that it diverges from the correct result, okay? And even Manton's method, it works up to some point that they start superposing, okay? After that, it can't predict what happens, so of course you need a numerical method, numerical simulation, to see what happens next. So then again we checked another thing, which is the acceleration as a function of the center of the kink anti-kink, okay, then you will see that in phi 8, if you look, the simulation and the Manton method solving it numerically without further approximation, they work really well, they match really well, okay, but our extra approximation to solve everything analytically for small separation, for small a, is not good, it is out, but as much as they get more separated, the center of the kink grows, which means that they are getting more and more farther away. The three methods match perfectly, okay, as expected, because then it goes to the asymptotic value. But then if this is logarithmic graph, so you see that how slowly it converges to that correct value when you do the further analytical approximation, if you want to have everything analytical. And for phi 12, we didn't do the further approximation. We did it with our numerical simulation and the Manton method, just directly solving that first order equation numerically, and they perfectly match. You can see here in the acceleration as a function of the center of the kink. Then, okay, this whole comparison with Manton method was valid for slowly moving kink, but then we wanted to solve for a more general case for any initial velocity. Then interestingly, you will see that when you increase the velocity up to really high velocity, there is no Bayan formation. They simply they collide and radiate away, okay, except for really close to that critical velocity that they start reflecting, okay. Really close to that, there is short-lived Bayan, and then after that they start reflecting. But this happens at really large velocity, ultra-relativistic velocity, okay. But then this is in sharp contrast with the result of the models with exponentially decaying tail, kink with the exponentially decaying tail, or one long range, okay, which is really interesting result because it shows that if you have double long range tail, or you have just one of the tail to be long range, they have really different results, because in the case of exponentially decaying and with one long range tail, you see always Bayan formation, and after that it can decay or reflect. But in our case, it is never appearing this long-lived Bayan, except for really close to this critical velocity appears short-lived Bayan, and then just after that appears this reflection at really large velocity. This is the result for phi 8. For phi 12, we couldn't get to that large velocity that has the reflection. We couldn't find the exact critical velocity, but we know that it's above this v 0.94 because it is even more long range than the phi 8. So if you have double long range, the point is after the collision, because now after the collision they start seeing the other tail, and when it is long range, the other tail, the system fast like a free field start losing energy, spreading energy really fast, so doesn't have enough energy to create again the Bayan, the kink and anti-kink together, okay. And if the velocity, initial velocity is that large, that gets really ultra relativistic, at some point becomes possible to have this short-lived Bayan, okay. And this is even worse for the phi 12 because it's even more long range. So we expect this critical velocity to be even higher than 0.94. But numerically, it's really difficult to get close to v equals 1, okay, the maximum velocity. So we couldn't get to that critical velocity for phi 12. So then the whole point here is that we did the collision with double long-range kinks. We did the Manton, we solved with Manton method analytically. Then for phi 8 was possible to do further approximation and solve everything analytically, but for phi 12 was not possible to do it analytically. So we looked at Manton method with this accelerating kink, but solving it numerically and compared with our numerical simulation, and they perfectly match, as we showed. And besides that, the most interesting result here is that there is no long-lived bion formation for any of these two models, and the reflection appears in ultra-relativistic limits for both models, and in the case of phi 12, it is even worse. Okay. Then I wanted to give you some notion what else you could do with the soliton. So besides the soliton interaction, you could have the interaction of the soliton with different types of fields, for example, fermion field. Okay, so you could consider something like this Yukawa coupling, or you could consider in a more nonlinear form with this exponentially they interact, or any other model. I mean, if it is a valid model, you could consider how the other fields like fermion field behaves in a background of a soliton, or even in interaction with the soliton. For example, if you have a soliton in the system as a background, and you introduce a fermion field there, you can create a bound state for the fermion. Okay, you can distort the vacuum and create even a Casimir energy. So you can do many things with the soliton fermion interaction, or boson soliton interaction can have many different forms. You could solve the system. You could consider the soliton as background or interacting with each other, like if you work with the weak coupling regime. As I showed, the mass of the soliton is related to the coupling, but to the inverse of the coupling. So in weak coupling regime, the soliton is highly massive. So the other fields, quantum fields that you have in the system, they will be behaving quantum mechanically, but the soliton itself could be considered classically as a background field, which is really heavy object, heavy particle-like object. So it doesn't matter, you don't consider the effect of the other fields on the soliton, because it's really heavy object, it doesn't receive much effect. So you could consider it as background. But you could consider not weak coupling, you go to a strong coupling limit, and in that case, you could study the interaction of the soliton with this fermion or boson field and see what happens to the fermion boson field and what happens to the soliton itself. There are many methods to solve this kind of interaction. You could even consider, instead of considering this interaction as a term in the Lagrangian, the interaction term in the Lagrangian, you could consider the soliton as background, for example, some people consider like this, and consider it that as a background that changes your effective space-time for the other fields that they are available in the system. Okay, and then you could work with the fermion or boson field in this. It could create curved space-time or not. Okay, but then you could consider this fermion or boson field in this type of background space-time, that it is like effectively what soliton does to your metric of the space-time, and in that metric what the other fields will see. Okay, so you could consider it this way or the other way around, that considering it as interaction term in the Lagrangian, and even sometimes people, they do from one to the other or the other way around. I saw some works that they start with the field in the background, for example, in a curved background, boson or fermion field, and then they see how they can translate this as an interaction term in in the Lagrangian. So there are a lot of possibilities to work with these solitons in different contexts. It could be in high energy physics to see different types of soliton, like cosmic string, for example. Or you could go to the condensed matter system, work with the different defects like disclination, dislocation, or different types of soliton, and see what happens to the other field. Here I talked about the boson fermion field, but even you could consider the gauge field there, like how the photon will see these defects in the system, for example. So this was to give you some idea what you could do with the soliton, and I hope it was useful for you.